Welcome to August's first LeetCode challenge, making a large island. You're given an n by n binary matrix grid. You're allowed to change at most 0 to be 1. Return the size of the largest island in the grid after applying this operation. An island is a 4 directionally connected groups of 1. So say you're given this matrix grid here and you want it to be island, right? Give me 2 seconds. So you have an island like this. You're at most you can change 0 to 1 to make what is the most contiguous island, which is basically 4 directionally connected groups of 1. And you want to return the number of that. So for instance, if you turn the 0 to 1, therefore you have this L shape right here, 1, 1, 1, which is size is 3. Right, likewise, you can always change this 1, 0 until 1. We have 1, 1, 1, which is size 3. Therefore, the output is 3. Right, you change one of the 1s to connect to the 2 1s, and they get an area of 3. Likewise, if you change the 0, if there's only 1 0 on the grid, you change that to a 1, then they're all connected, so therefore the output is 4 because you changed this 0 into a 1. Likewise, here you don't have to change a 0 to a 1. If they're all 1s, that means you can't change any 0s to a 1, so the island area is equal to 4. So that's basically the gist of it, is making sure that you change 1 0 to a 1 if possible to make the most biggest island connected by 4 directionally connected group of 1s. Alright, our constraints is n grid length, n is so squares is n by n, n is between 1 to 500, and ij is either 0 or 1. Alright, so my approach to this is going to be basically a naive depth first search approach. Because for each 0 in the grid, let's temporarily change it to a 1, then count the size of the group from that square. So basically we're going to change each 1, count the size, and store the max basically. And then we just backtrack, change it back, and then just continue until we store the max. So for each 0, what we're going to do is change it to a 1, do a depth first search to find the size of that component, then return the maximum size of that component found. Of course, if there's no 0, then the answer is going to be the size of the whole entire grid. So this is not really the best, most efficient way of doing it, but it's a hard question, so I'm just gonna give the bare minimum here and see what I can do. So first thing we're gonna do is find n, right? So n is gonna be, since n is gonna be the length of the grid, and then we also want to find the frequency as well. How am I gonna describe this? The frequency, yeah. So we're gonna find the index, I should say. It's called index, and that's gonna be 2. So if we do change each 0 to a 1, then we find the largest size. Actually, what we're gonna do is every time we check a 0, we also store the size of each group so that we don't have to use depth first search repeatedly to calculate the same area. So instead of storing individually the max, we could actually keep track of a group of IDs or index here, so that it's unique for each group. So that means that each component size is unique, so we can store it in a stack. So then only add the areas of the neighboring groups with different IDs. So for this algorithm, just improving on the naive depth first search, what we could do is for each group we fill it with a value index, and then we remember the size of the area at the index using depth first search. Then for each 0, we look at the neighboring ID if it's already visited or seen. Then we store those groups into a 1, and then we toggle it to then we change it from a 1 for the 0. Then we toggle it. This gives us a candidate for an answer. Then we'll take the maximum. So potentially, if there's no 0s, then we take the maximum of the previously calculated areas. So actually, this is actually using a depth first search improved with using component size indexing. So we have something called a variable called frequency. And that's going to be assigned to default dict. Default dict with index. Integer. I'll show you this T there. Alright. Now we're going to do a for loop here. So basically this is our essentially defining it, looking for the neighbors, I should say. So for the row and call it R in range of n, for column in range of n, if the grid at row and column is equal to 1, then we're going to add that to a stack. Stack that to row column. There you go. We're going to add that row column index to our stack. And then we are going to also change that grid row column to our index. So while the stack exists, what we're going to do is we are going to define, we're going to pop some values here. So we're going to do I, j, stack.pop from the end, pop from the end of the stack. And then we're going to do is frequency of the index. At the index value, and we're going to assign that to be incremented by 1. So we're basically increasing our index, our frequency at the index. Because just remember, we're storing that as well. So for each direction that we travel in, so this is when we're traveling through our grid, see how to calculate the size of it. So let's call it dx dy, changes in x and y direction in the I minus 1 direction j. So this is traveling basically downwards. Yep. And then ij minus 1, ij plus 1, and then we have I plus j, 1 plus I plus 1 j. I'm actually gonna change this. Alright, so for the changes in x and y direction, each of the directions, coordinates, if 0, if the changes in the x direction is greater than or equal to 0, and less than n, and likewise with changes in the y direction, dy less than n, and the grid at the changes in x and changes in the y direction equal to 0, then we're going to stack dot append that coordinate index, I should say. Append. I'm going to append dx and dy, and then we're going to change the grid at dx dy to our index. And then we want to be able to increment our index as well. So essentially, this is what we're doing. We're going through our rows and columns. So this is a nested for loop. So if the row and column is equal to 1, what we're going to do is we're going to update our stack with basically we're storing all the number of ones in the grid. So we're storing all number of ones in the grid into the stack, and we're storing the grid at location row and column and make that an index. So while the stack exists, we're going to pop the I and j coordinates, whatever stored in there, from our stack, and then we're going to increment our frequency by 1 at the index I. So next we're going to do the same thing. Basically, we're looping through our changes in x and y direction, and we're incrementing. We're looking to see if x is between these values and y is between within the bounds, and if the grid changes at x and y direction is equal to 1, then we're going to also append it to the stack as well. So this is we're changing it, we're changing the direction, the cell into a 1. See if the index matches. And then what we're gonna do is we've already made our changes. Next thing we're gonna do is gonna use our answer. So I'm gonna define output, and it's gonna be max of the frequency dot values, and then it's gonna be default to 1, a 0. If there is none, 0. So next thing we're gonna do is do a for loop. I should probably put this down. We don't need space here. Alright, so for I in range n, for j in range n, we're gonna go through the loop and go through our nested for loop entire grid and search basically if the grid itself is I j is equal to 0. Because remember, we did the first time. Now we're looping through a second time. So these are going to be in running side by side. So it's not going to add to the overall complexity, time complexity that much. We're going to look for a candidate, and that's going to be 1. All right, and then we're going to have this thing called visited, and it's going to be a set. So for changes in x, y, changes in y, in our coordinates, copy this, the same line almost. So if changes in x and y, let's see. So if changes in y is greater than or equal to 0, but less than n, and same thing with y, less than or equal to greater or equal than changes in y, less than n, and the grid itself in the changes in x and y direction, and grid at changes in x and y direction not in visited. If these conditions are met, right, changes in x direction has to be equal, within the bounds. The change in the y direction has to be within the bounds as well. Because remember, we're at this location, we're traveling up and down, so we're basically counting our islands, if it's a 1 or not. Then what we do is visited, and then we add that area. So we add that grid point to our visited list because it's something that we have already checked. Alright, and then we increment our candidate to be incremented by our frequency at the grid at location changes x and dy. Alright, and then our output should be our max between our output and our candidate. And then we want to return our output. Let's see. Let's submit it. Okay, accepted. Awesome. So this is quite a long and tedious and complicated one, but overall, you're basically we have the naive approach, that first search. We're basically changing each 0 into a 1. Not each 0 to 1. We change the grid itself. We scan through the entire grid. We change it to each 0 1. We keep we change a 0 to a 1. Then we count how big the island is. Then we keep track of that. And then we do it again. We just reset it, and then we change the other zeros to a 1. Then we count all the biggest island possible, and then we return that. So basically, we're keeping track of the component size using the index number here. And then basically, what we want to do is for each of the, we fill in the values of the index, and remember the size of the area, the frequency of the area of the index, using depth first search as we do. And then basically we just take the maximum of the previous calculated candidates, and then we just find the max between that. So overall, this is a, let's see, it's 1, 2, 3, 4. So it's actually still basically pretty much a naive approach actually, using depth first search. So overall time complexity is big O to n to the 4th, where n is the length of the grid and width of the grid. So space complexity, we have a stack visited, and then we have a visited set, which is being stored, and we also have a stack. So big O of n squared. Additional space being used by depth first search by stack and visited for time space complexity. Well, this is a hard one and long and messy, but there you go. Hope you guys have a nice day.